Section 3 is operations on functions, and there are 5 operations that you're going to be asked to compute with functions. Those are addition, subtraction, multiplication, division, and composition. And it's important you can recognize the different notations that are for each type of operation. So addition, there are 2 different ways the notation can be written. Typically, it's going to be this first one. So f plus g of x. But you could also see it as f of x plus g of x. And both notations represent addition. Similarly, subtraction can be seen as f minus g of x or f of x minus g of x. And for all of these operations, the first notation I write is typically going to be the notation that I'm going to use in problems. But the second one is also possible. Now we're talking about addition and subtraction. Remember back to with numbers, the order of addition doesn't matter. So f plus g of x is the same thing as g plus f of x. However, subtraction order matters. F minus g of x is not the same thing as g minus f of x. So it is important the order in which I write the functions for subtraction. So moving on to multiplication and division, similarly, 2 notations. So multiplication, f times g of x or f of x times g of x. Division can be seen as f over g of x or f of x over g of x. And for division, it's important here that g of x does not equal 0. In a function, I'm not gonna be putting 0 in the denominator, but it's an important distinction to make. So similarly, as addition and subtraction, there are rules to the order of multiplication and division. So order of multiplication, like addition, does not matter. F times g of x is the same thing as g times f of x. However, for division, f divided by g of x is not the same thing as g divided by f of x. So order for division matters. Last operation is composition. So notation for composition is f of g of x or f of g of x. So they're said the same way, but they are not written the same way. Both mean composition. And again, you're going to see this first notation most of the time. And just like subtraction and division, order of composition does matter. F of g of x does not mean the same thing as g of f of x. So those are the notations for the operations. Now let's do some examples. We're not going to do every operation. We're just going to do a few of them. So given the functions f of x equals 2 over x plus 1 and g of x equals 3x minus 4, the first thing we're going to do is write the domain of each of those functions. So when writing the domain of our function, we always identify the parent function for each of them. So this is all the way back in section 1 where we talked about domain of parent functions. So our first function, f of x. Since we have a variable in the denominator, its parent function would be the rational function. And from section 1, we know rational functions are not defined when the denominator is 0. So I have to figure out when the denominator is 0. So when does x plus 1 equal 0? Well, I subtract 1 from both sides. It's when x equals negative 1. So for f of x, its domain is all real numbers except when x is negative 1. So x cannot equal negative 1. For our second function, g of x, which is 3x minus 4, its parent function is our linear function, and linear functions domains are all real numbers. So its domain all real numbers. Let's go ahead and do some of our operations. So first we want to find f minus g of x. And once we find that, we're going to identify its domain. So f minus g of x. So order matters. So first function f, 2 over x plus 1 minus 3x minus 4. And when performing subtraction, I would always put the second function in parentheses, because remember, this subtraction is applied to the entire function, so it's applied to all of 3x minus 4, not just the 3x. I'm going to wait to distribute that negative, because in order to perform subtraction, you have to have the same denominator when dealing with fractions. So I'm first going to rewrite 3x minus 4, so it has a common denominator as 2 over x minus 1. So to have a common denominator, they both must be x plus 1. So I'm going to multiply it by x plus 1 over x plus 1. So now I'm really doing 2 over x plus 1 minus 3x minus 4 times x plus 1 over x plus 1. I'm still going to wait to distribute that negative. I'm going to go ahead and distribute 3x minus 4 and x plus 1. But I'm going to go ahead and write it as a single fraction now. So I'm going to have 2 minus, I'm going to do my distributing, so 3x times x, 3x squared, 3x times 1 is 3x, negative 4 times x is negative 4x, negative 4 times 1 is negative 4, all over x plus 1. So now you have two options. You can either combine like terms before distributing the negative, or distribute the negative first and then combine like terms. So I don't have to combine like terms first. I'm going to go ahead and distribute the negative. So 2 minus 3x squared minus 3x plus 4x plus 4 all over x plus 1. So when I combine like terms, I'm also going to reorder it, so it's written in descending order. So f minus g of x equals negative 3x squared, negative 3x plus 4x is x, plus x, then 2 plus 4 is 6, plus 6 all over x plus 1. So this is my answer when I subtract my two functions. Now I want to identify the domain of this function, of negative 3x squared plus x plus 6 over x plus 1. So I need to identify its parent function. I've got variables in the numerator and denominator, but because there's a variable in the denominator, its parent function is my rational function. So just like when we're finding the domain of f of x, I have to figure out when the denominator is 0. Well, because it's the same denominator, I already know the domain. So the domain, all real numbers, x cannot equal negative 1. That is possible. You can do an operation and get a domain that's still the same as one of the original functions. So now we want to find g divided by f of x and its domain. We're still dealing with the same two functions. So f of x is still 2 over x plus 1, and g of x is 3x minus 4. So I said the order of division matters. So because it's g divided by f, g is going to go in the numerator, f in the denominator. So g over f of x equals 3x minus 4 divided by 2 over x plus 1. So because we're dividing by a fraction, in order to simplify it, I'm going to rewrite it as multiplication. So my numerator is 3x minus 4 over 1. And when I rewrite it as multiplication, I take my fraction in the denominator and multiply it by its reciprocal. So I'm multiplying by x plus 1 over 2. This is the same thing as the division written above. So now for multiplication, I just multiply straight across. So 3x minus 4 times x plus 1. So I'm going to distribute. So like before, 3x squared plus 3x minus 4x minus 4. And my denominator, 1 times 2 is 2. So now all I have to do is combine like terms. So final answer, g over f of x is 3x squared minus x minus 4 all over 2. This is the answer when I divide the two functions. Now to identify its domain. So even though I'm dividing by something, I'm dividing by a number. So it is not, the parent function is not the rational function. So now I just have to look at my numerator. Well, my numerator is a quadratic, so its parent function is the square function, whose domain is all real numbers. So my domain is all real numbers. Next example is composition. So we want to find f of g of x. So as a reminder, composition is evaluating a function with a function. So if I want to find f of g of x, whatever is written second, you replace the variable in the first function with the function. So f of g of x has to take my function g and plug it in for every x that appears in f. So f of g of x, so 2 over, and then instead of x, I'm going to replace it with my function g, so 3x minus 4. And then I still have plus 1. Now because there's a 1 out front, if I multiply it by 3x minus 4, I get 3x minus 4, so it's 2 over 3x minus 4 plus 1. Now I can just combine like terms. So my final answer, f of g of x, is 2 over 3x minus 3. And I'm not going to do the domain of the composition at this moment. So our last example is to evaluate one of our operations. So I want to find g of f of 5. So there's two ways you could approach it. You could find f of 5, then plug it in for g, or you can find the composition g of f of x, then plug in 5. Both should give you the same answer, but I'm going to go ahead and find the composition g of f of x first. Then I'm going to go ahead and plug in 5. So g of f of x, as I said, is not the same thing as f of g. So second function plugged into the first. So I'm going to start with writing g, so 3, then it's x. So I'm going to replace that x with my function f, so 2 over x plus 1, and then minus 4. I'm going to go ahead and distribute the 3. technically this 3 is over 1, so when I multiply it, I multiply 3 times 2, which is 6. My denominator stays, x plus 1, and then minus 4. And because my goal is to evaluate this composition with 5, I'm not going to simplify it any further. I'm going to go ahead and plug in 5 for x. So g of f of 5, now I'm going to replace every x with 5. So 6 divided by 5 plus 1 minus 4, which becomes 6 over 6 minus 4. 6 divided by 6 is 1, so 1 minus 4. And finally, g of f of 5 is negative 3. And if I had found f of 5 first, then plugged it in for the x and g, I would have gotten the same answer as of negative 3.